Alrighty, welcome back to operating systems. So, any questions, comments, concerns about the last lecture, or are we all okay with page tables before we make it approximately 3 times more complicated? Okay, well, we have a little bit of a problem on our hands. So, we know we divided our memory up into these big blocks. So we divided the whole of memory. Okay, we're going to do this again. So if this is all of physical memory, right, we divided it up into a bunch of blocks. And then the size of each of these blocks was like 4096. But we have a little bit of an issue, because we need to also store the page table somewhere in physical memory as well. And currently, our issue is it is absolutely gigantic. So remember, for a 39-bit address with our 4K page size, our page table needs to have 2 to the 27 entries. And each of these entries, remember, contains at least a valid bit and the physical page number. So this is basically a giant array. So there is 2 to the 27 elements, and each page table entry in here, so each row, if you want to think of it that way, is 8 bytes per page table entry. So how big is this page table in bytes? Yeah, 2 to the power of 30 bytes, right? So this is how many entries I have. And then if each entry is 8 bytes, if I write that in powers of 2, that's just 2 to the 3. So the total size of it would be 2 to the 27 plus 3, aka 2 to the 30, aka 1 gigabyte. And this page table, that would be the virtual to physical mapping for one process. So 1 process, and our page table is a gigabyte. So, yeah?
For clarification, 2 to the power of 27, does it represent the number of pages or the number of entries in one page?
So yeah, the question is, 2 to the 27, is that the number of virtual pages or number of entries in the page table? And the answer is, it is both. So it's the number of virtual pages, and each virtual page needs an entry in the page table to tell us what physical page it maps to. So same answer for both. All right, so this is obvious. This is kind of bad, so we'll be solving this problem today because, well, if I had 16 gigs of RAM on my machine, and I have 16 processes running, and I have a page table per process, how much room do I have for applications to use? 0. Is that good? No. So we're going to have to do something to solve this. So the first idea could be that, okay, well, also to make things simpler, since, you know, we've already divided our memory into blocks and we need to store them somewhere, well, first idea might be like, hey, why don't I just use these pages themselves? Why don't I just use these pages themselves to store the page table? Like, it has to be in memory anyways. If I've already divided memory up into blocks, I should probably use the blocks to store the page table. So our first step is going to be to just make a page table fit on one block. So that will obviously limit how many entries we can store in the page table. So here I would argue that if my page table is 4K or 2 to the 12, then I can only fit like 9 different entries in my page table. So why is that? So basically, I'm constraining it so that the total size of the page table now, instead of being this, right? I want it to just be the size of a page, aka it should be 2 to the 12 or 4 kilobytes. So if this is the total size of my page table, I should be able to figure out how many entries I can hold in a page table. So I would just take the number of the total size of my page table and then divide it by the size of an entry. So in this case, it's 8 bytes an entry. So if I keep it in powers of 2, I can easily do the little exponent law and figure out that it's just the same as 2 to the power of 12 minus 3, which I can do math on, and that is 2 to the 9. So that means if my page table, if the size of my page table is 4K, that means I can only fit 2 to the 9 entries in it. So everyone okay with that? All right. So that is what I'm going to do here. Obviously, now how big of a virtual address can I support here? How many bits can I use for a whole virtual address? Anyone add the 2 numbers at the top? So my virtual address here, right, is just the 2 numbers at the top. So I can only, it would be 9 plus 12, which is 21. So that means I could only support up to what? 2 megabytes of memory with this system if my page table only fit in a page. So that's our major drawback here. So we're going to have to do something about it. But for now, our idea is we want our page table to fit on a page. And our physical address, since the PPN stored as part of the entry, it doesn't change. It would still be 44 bits based off what we argued about before. And then since each process has its own page table, there's actually a register on your CPU that the kernel is going to control that tells your MMU which page table to use to translate virtual addresses for this process. So before I continue, anyone have any problems with this? Same thing as yesterday, but now my page table fits on a page, so it is much smaller. Alrighty, so now we are going to take an adventure to this. So this is how we extend that idea to actually support all 39 bits of virtual address space. We have multiple levels of page table. So this will make translating an address a bit more complicated because we split it off a few different ways. So now we take that virtual address and instead of, where's my mouse pointer? So we take this virtual address and instead of just having all of this for the virtual page number, we split it out into multiple levels. And each level of this page table will fit on a page. So now to translate the address, we have to go through a bit more hoops. So the top 9 bits here, that will give you the index into the first L2 level page table. So we just creatively just give them L number for their names. So the root page table would start here. I would find based off the index I get from these bits of my virtual address, that will tell me which entry to look up here as before, and it will tell me what the physical page is for this index. But now instead of using that to translate the virtual address to a physical address, instead, now that physical page tells me where the next page table is. And then I use the index, the next 9 bits for the L1 index to find what entry I should look at. That entry will also tell me a physical page number. And then that physical page number will tell me where my L0 page table is, which is the lowest level, which actually has the physical page number for this virtual page. So L1 or L0, that will have its page table entry. It will have a physical page number like the other ones, and it gives me the actual physical page for this virtual address. And again, Mercifully, we don't have to translate the offset. So, everyone okay with this? Yeah?
Sorry, the L2 page table points to the entry in the L1 page table?
So the L2 page table, which entry you access depends on the bits here, just like for before with a single page table. But instead, before, the entry told us what physical page this virtual page mapped to. But now in this case, it tells us what physical page the L1 page table is on. So it tells us which page table we need to access. Yeah?
So I thought these bits were the index to the page, because like there are multiple pages, and an index which page you're accessing.
Yeah.
But now what's happening now then?
So now before, like all the bits together, which was the whole virtual page now, right? But now we split it up into multiple levels. So now instead of just indexing a giant table, we split off the index to other tables and they lead us to other ones. So for like here, I use this part of the index to tell me which entry in the first page table that fits on a page goes to. And then I keep on following it over and over and over again until I eventually hit the last level here. So drawing it out a bit, so let's see if we can draw it out a bit. So before, assume our memory is just in blocks. So if we just had a like massive page table, right? It might just span every single block and just take up everything, right? And then, well, it would be easy because whatever index we use, it just tells us exactly where we go and whatever page we find it on. Now, each page is itself its own little page table, so it can't possibly have an entry for every single index, right? It can only have 2 to the 9 of them that fit on a page. So I have, in this case, 2 to the 9 different options here. And then each of them will point to a different L1 page. So maybe at index 0, it points to this one. Maybe at index 1, it points to this one, right? And then I have to use the next bits to pick which entry in this page table I need to access. Oops. So this is an L1, this is a different L1. So maybe, I'm accessing 188, and that will tell me which page table I have to access for an L0. And then maybe that has another entry at entry 5 or something like that. That tells us where the actual page is that's used for data. And this doesn't give me any less indexes I could have. So before, right, I had 2 to the 27 before, right? So this is a bit more roundabout way, but I don't have any less indexes because in this L2 page table, how many different entries are there? 2 to the 9, right? And then for each of those 2 to the 9, right, this could point up to 2 to the 9 things. How many different things could each L1 page table point to? 2 to the 9, right? And then how many different pages could each L0 page table point to? 2 to the 9. What's 2 to the 9 times 2 to the 9 times 2 to the 9? 2 to the 27, so it's the same thing, right? I'm just splitting it up a bit differently.
What would be the benefit of splitting these up now?
Yeah, so what is the benefit of this? So before, when we had that massive like 1 gigabyte page table, if I wanted to translate a single address, I needed a gigabyte page table, right? How much memory do I need to translate a single address now? So to translate a single address, I only need 3 pages now, right? So if I wanted to translate a single address, well, I could have an L2 that leads me to an L1 that leads me to the L0, and then that has my final physical page for this virtual address. So I can actually translate a single address with only 3 page tables here. I only need 1 for each level to translate a single address. Yeah?
So I just have a question. Since you have 9 bits, like for example for L2, to indicate which L2 page table you're accessing.
So L2 tells me which L1 page table I access.
I'm talking about the virtual address.
Yeah.
So do you automatically know which L2 page table you're accessing?
Yeah. So the question is, how do I know which L2 page table I'm accessing? And that's what that SATP register is. That tells you your root page table. That tells you what L2 page table you need. Yeah.
So I'm just trying to get a hang of like how many of each level you need. So like because the L2 page table points to the L1.
Yeah.
Right? And we know there's like for each entry in the L2 page table there's how many? There's 8 bytes, right?
8 bytes. Oh, for each entry, but they all fit on a page, right?
Right.
So they're all 4 kilobytes.
Also, so how many? Like I'm saying, the entry that we're reading from the L2 page table, how many bytes does it have?
The entry itself, it's the same as before, 8 bytes.
8 bytes. So then, how many different L1 page tables can we have?
We can have up to 512 different L1 page tables. So for this, yeah, it's a good question. So for this, there will always be exactly 1 L2 page table. That's all you need. And then we can kind of figure out that this will actually waste some space too, in the worst case. So tablet. So there's always 1 L2 page table, right? It's always 1 L2 page table, and it can point up to 512 L2 tables, right? And then each of those can point up to its own 512 of them, which would be math. To the 18 is whatever the hell 2 to the 18 is. So you can have 2 to the 18 different L0 tables, right? And you might notice here that if this is all full, how much memory does this waste? So if I had 2 to the 18 different L1 page tables, and each of them fit exactly on a page, right? And each page is 2 to the 12, how much memory does it waste? 2 to the 30 again, right? 1 gigabyte, because, well, if we had 1 massive page table, we would be wasting 1 gigabyte. If we want to translate the same number of addresses, we just need to store the same amount of information. So this would actually waste slightly more information if we have to translate every single address. Yeah.
So I have a question. Is this for, so does each process have its own set of L2, L1, L3 tables, or is it shared?
Yeah, so each process would have its own like its own L2 page table, and then the operating system can decide whether or not processes share memory or not. Typically, each process the easiest thing to do is each process has its own unique L0 or L0, L1, L2 page tables. And then the actual entries the operating system will manage the entries so they can actually share memory if they need to. So, everyone okay-ish with this? So, drawback here that we already noticed is that, hey, if we would need to translate every single address, because we have multiple levels, we're wasting more memory. But the big benefit is, how many programs do you know that use 512 gigs of memory? Chrome, that's 1. Nothing else. How much memory does your program use? Probably like a few kilobytes, right? So instead of having a gig page table, I, at minimum, to translate a single address, only need 1 L2 page table, 1 L1 page table, and 1 L3 page table. So which is, if each are 4 kilobytes, then that's only 12 kilobytes for page tables. Everyone see the benefit here? We went from 1 gigabyte to 12 kilobytes. So, everyone okay with that? Yeah.
So the OS only assigns like page tables if you need it?
Yeah, so the OS will allocate page tables if it needs it for your process. And we'll see how to manage that a little bit. So yeah. Oh, yeah.
I don't really get what you mean by one L2 table points to 512 L2 tables.
So, slide. So here in this L2 page table, right? So when we just said everything fits on a page, that page table can have 2 to the 9 different entries, right? Where each entry points to, it has a page table entry, which basically tells us what physical page we're accessing, right? So there's 512, so that's why I said, since there's 512 entries here, and they each point to a page, and each L1 page table takes up a page, I could, yeah, from 1 to 1, yep, yep.
Are those page tables same size or like slightly smaller?
No, everything fits on a page. So every L1 page table, L1, L0, L0, all fit on a page.
So it's like 3 equal, like 3 to the power 9, or 2 to the power 8.
Yeah, so they each fit to the power 9 entries.
Okay.
Yeah, and we need 3 of them.
Does that make the memory faster?
So does it make the memory faster? So that's a really good question too. So when I had a single page table, how many memory accesses did I need to actually translate an address? Trick question, it's 2. But, so I have 1 to look up the entry, right? And then I have another for the original access. So you typically count the original access. So instead of, if I use normal memory, it would just be 1 access. If I use virtual memory in this case, I have to find the entry and then touch the memory, so I have 2 accesses. How many memory accesses do I need for this sucker? In total. 4, right? So I have to look up the entry in the L2 page table, that's a memory access. Look up the entry in the L1 page table, that's a memory access. Look up the entry in the L0 page table, that's a memory access. And then my original memory access once I have the physical address, 4. So remember, one of our goals was this should be as fast as using physical memory, and I, so far, have made it 4 times slower. But in making it 4 times slower instead of 2 times slower, I now do not waste as much space if my processes don't use that much memory, if I don't need to keep track of that many mappings. But yeah, I've made it much slower. But this is how memory actually works, and we will address this problem because this is a fairly easy one to address. But right now, really slow. All right, everyone okay with our slow system that actually saves space? It's the trade-off we made. Okay, so you might have wondered before, like, how do I allocate memory? Well, turns out if you just allocate in pages or big blocks of memory, one is as good as any other, and you can just write your own allocator. You have the skills to do it now. You just need a linked list. So you just have a free list of pages. So the unused pages themselves, they can actually store the pointer to the next unused page. So it doesn't actually waste any space in memory. You're using unused memory to store your pointers. So this would be initialized as boot. You can just set initially all of memory being free. And then to allocate a page, it is very easy for the operating system. It just removes it from the free list, uses it as a page, and then to deallocate it, all it does is say, okay, you're not using it anymore, add it to the free list. So memory allocation, really easy if everything is the exact same size and one is as good as any other, and you don't have to worry about it being contiguous or anything like that. So that was our insight. We used a page for each smaller page table. Again, for this scenario, we would, since they all fit on a 2 to the 12 size page, we would have 512 entries, which is 2 to the 9, and our page table entry size is 2 to the 3. So everything makes sense that fits on a page. So if you get a question for this, just remember, this is how we do multi-level page tables. So even if I change the entry size or the size of the page, you should be able to figure out the last variable here. And the general way of doing this is, no matter how many levels of page tables I have, the page table entry for L to the n always points to L to the n minus 1. And then you follow these as many levels as you need, eventually until you get to L0, which contains the physical page number that you actually wanted to translate this virtual address for. So here are some other ways to think of them. Think of them just like an array. Like, people get very confused about it, but before, if I had, say, an array of 512 ints, what's the size of that in bytes? Anyone remember? Yeah. Yeah, 2048. Why? Because, well, it's an array. There's 512 elements or entries in it. The size of an int is 4 bytes, so it's just 4 times 512. So it's just 2048. And then for offsets, well, if each int is 4 bytes, and I'm accessing the int at index 2, what byte does that int start at? 28. Which one? 8, right? So because arrays are 0 indexed and computers like, having 0 indexed, the first offset, the first byte would be at byte 0, and then since ints are 4 bytes, the next byte would start at byte, or the next int would start at byte 4 at index 1, and then the int at index 2 would start at byte 8. So same idea for page tables and everything. Offset is just number of bytes from the beginning. So you will think of a page table as just, an array of page table entries, no different than having any other array you've seen in your life. So if we have a page table, we have 512 entries in it, and it's like an array of page table entries. Well, for this scheme where each page table fits on a page, the size of the page table better be equal to the size of the page. And the size of the page table is just simply the number of entries times the size of the page table entry. So all these numbers, those two equations should always be true if we have multi-level page tables. So everyone okay with those? Yeah. Yeah, so in this case, my page table entry would be 8 bytes. But older systems, the page table entry was actually 4 bytes. But since we have much more memory now, it's 8 bytes. All right, so let's do some translation with multiple levels. Ooh, fun. So I'll just go and start an example. So we're going to assume a system with just one more level of page tables. So if we looked at the virtual address, okay, we're doing this. So if we looked at the virtual address, if we just have 2 levels of page tables where we only have an L1, that looks terrible, an L1 and an L0, that is longest night. Wow, okay. I'm going to throw this thing in the river. Okay, so if we only have 2 levels of page tables, there'll still be 9 bits, right? So just like here, all I'm doing is I'm chopping off L2 because I don't want to deal with it. So everyone okay with that? We can make it just 2 levels of page tables, so my address, I can only support what? A 30-bit virtual address. All right, so of my virtual address, my L1 and L0 will both be 9 bits to tell us where we go, and then the last 12 bits is my offset that I don't have to translate. That is the wrong thing. There we go. So that is how my virtual address is kind of set up. So now if I have the virtual address, let's say we want to translate 3 F 008. 1, 2, 3, 4. Yeah. So say we want to translate this virtual address. Well, we have to figure out what index we use for L0 and L1, and we also need some other information, right? So in order to translate this address, I need some more information. So I would need to have, as part of my system, I would need to know which L1 page table I need to use for this translation. So that would be stored as part of that process as like the root page table. So maybe my root page table, it has an entry at, I don't know, 512. That equals, that tells me that the physical page number is 8 or something like that. So first off, from the virtual address, I should probably figure out what indexes I need to use for L1 and L0. So how would I do that? Kind of like we did yesterday where I had to write all the binary, right? So for that, my offset is 12 bits. So what do I not have to translate? Yeah.
008.
Yeah, 008. So this is my offset. I don't have to translate it. The rest of them, since doesn't line up nice with hex, it's 8-bit or 9 bits each. I probably have to write it out in groups of 9. So luckily, 3 is just 1, 1. Oh, I was writing black. So 3 is just 1, 1. Then F is just 4 ones again, right? And then 4 ones and 4 ones. So 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. So that, all those bits represent 3 F, 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 right? That's a lot of F's. So now we group in 9. So this tells me my L0 index. And then this, or the rest of them, I think I missed an F. 1, 2, 3, 4. So this is the other 9 bits, right? They're all 1 as well, and they tell me my L1 index. So as part of translation, there would be a register that tells the MMU, the memory management unit, what L1 page table, in this case, do I need to start off my translation? So if in my L1 page table I have an entry at index 511, so this all 9 ones is 511. So that means in order to translate this, I have to look at the page at page 8 to actually get my information for the L0 page table, right? So say the root page table lives at address, say it lives at 7. So in memory, page 7, that would have my L2 page table. Somewhere on it had an entry for 255, and that told me here that to find the, L1. So to find the L0 page table, I have to find it on page 8. So page 8 would have my L0. And then I would also have to tell you that, hey, consider L0 on page 8. And say it also has an index, it also has an entry index at index 512. That points to physical page, I don't know, let's say cafe. Or CAFE. So, yeah.
I don't understand what you meant by page 7, page 8.
So this is the physical page number. That's basically just telling me which physical page it is. So I can just start naming them from 0 like anything else, right?
So 0x8, but then how did you get to X7?
Oh, so I just said initially I assume that the root page table is on page 7. So that's where L1 is. And it could be anywhere. All right. So in order to get my final physical address for this virtual address here, what is my final physical address? So before, when we had one page table, right, all we did is we looked up the physical page number, just replaced the virtual page number with the physical, kept the offset the same, and that was our address. So this time, the only change to the process is I split up my virtual page number into a whole bunch of different indexes because it's stored on different pages. But at the end of the day, in the L0, I get my physical page number, and it's the same thing. I just want to replace the virtual page number with the physical page number. So the entire virtual page number before was this, right? Was 3FFFFFF. And then going through, eventually finding in L0 that my last physical page number was this. What is my resulting physical address for the virtual address 3FFFFF008? Yeah. Yeah, just CAFE with the offset from before, right? We don't translate that. So my final resulting physical address, in this case is CAFE008. Whenever you get to the entry in the L0 page table, that tells you what physical page is used for this virtual page number. Yeah?
So then if you gave us all of this information about like the physical address, the PPN for the physical CAFE, we didn't need to do any of this. You could have just took CAFE, took the offset, and just concatenated them, right?
So in this case, this CFE was on a page, right? Part of a page table entry, but there's no way you can just immediately leap through it without going through L1, right? Because I could change it that this entry, say I did something silly and had it point to itself. So if I made it point to itself or something weird, then my final translation will not be this. I'll have to go through the procedure. So this would tell me, where the L0 page table is, and it turns out to be itself. And then it would look at that entry, and then it would get this as the physical page number, and our resulting address in that case, if I did something that silly, would be 77, something like that. So it depends. But all I need, I have to tell you a bunch of information in order to actually translate an address. I need to tell you, at minimum, the root page table, the virtual address, and then I have to tell you the contents of every single page for you to translate it. Yeah.
Just a question. When you're going from L1 to L0,
Yep.
and you calculate
Yeah.
So then what happens to the original, like 0x3, like what happens to that? Do we put 0x8 and then we translate that as well?
No, so from the virtual address, we only use the indexes. We use the indexes and then the L1 page table, and then past that, we don't use the virtual address for anything else. We only get the indexes from that, like before. So like,
So we will use the L1 index to just know that it's the 511th entry.
yeah.
And then we take 0x8 and what do we do with it?
So we know from the index we have to look at the 511th entry, and then since it's in the L1 page table, that tells us where the L0 page table is. And then to look up the index for L0, we're going to use that page table and then the index from this virtual address. So we have to look at entry 511 from that page table. And then that gives us, since it's L0, that tells us where in memory this virtual page maps to.
But just to clarify, you told us that the 511th entry of page L0 was 0x8, right?
Yeah, I told you that. Yeah, so I'd have to tell you like what the values are in memory, otherwise you couldn't translate it, right? Yeah, I'd have to tell you. Yep.
This L1 not L0, or
Sorry?
this L1 not L0, like you use the virtual index to map L1.
No, so just every entry in L1, in this case, points to an L0 entry.
Okay, so it's L1 not L0.
Or sorry, points to an L0 page table, not an entry. So by default, you're given the L1 page table, and then from the virtual address, you know which entry to look up. This entry tells you what L0 page table to use. Use the virtual address to figure out what entry in the L0 page table you need, and then that tells you the physical page number for this whole virtual address. Okay, everyone okay-ish? This is everyone's favorite topic every year. As soon as I do 3 levels, people break. But, so same idea, we'd have the same idea for, this is 2 levels, but it would be the same idea for 3 levels, just harder. All right, everyone okay-ish with this? So, in order to help too, I have a little simulator I wrote. So, this will hopefully also help. So, I wrote a function called allocate page table. All that does is give me a new page. And then I wrote a bunch of helper functions so I can, create a page table entry for a physical page number. So, I'm assuming that all of these page tables, or all the memory I get, they're physical addresses. So, in order to do a translation, so this is going to be 3 levels of page tables. So I'm going to do something like this. So I'm going to translate a single address, I need an L2 page table, an L1, and an L0. So here I'm going to allocate a page table. So in order to translate an address, I need like a root page table. That would be an L. In this case, if I have 3 levels of page tables, it would be an L2. I only have 1 L2 page table. So I would set that as my root page table. That will be used to actually do the translation whenever I try and access virtual memory. So I set it to this page table, and then I create an L1 page table. So this allocate function just gives me a new block of memory. And then in my L2 page table, I have to point to it. So in this case, at index 0 in the L2 page table, I have this function page table entry from page table. So it will basically just take this address for this L1 page table and then just turn it into a page table entry. It basically just extracts the physical page number for me and tells me whether or not it's valid. Then here, since I'm translating a single address, I need an L0 page table. And then in the L0 page table, in the L1 page table, at index 5, and we'll see why I use exactly these indexes, I point to an L0 page table. And then in the L0 page table at index 188, I create a page table entry that tells me that the physical page number is CAFE. So now, if I run this MMU function, I give it a virtual address, and it should spit me back out a physical address using the root page table and the virtual address, and that's the only information I give it. So, any questions before I run this and we figure out why it says what it says? So, if I run this, I get that virtual address ABCDEF actually maps to CAFE-DEF. And then for the other one, I get a page fault, AKA it doesn't have a valid mapping. It doesn't actually, that would be your seg fault, that would be you accessing memory you're not allowed to access. So, anyone guess why this one translated? Why did this address translate to CFDE, knowing how I set up everything here? Oops. So here, right. So just looking at that, everyone figure out the indexes all make sense and everything's all good? All right, let's make sure I wasn't crazy. So, same thing is going to happen. So, if this is my virtual address, right, I still have to divide it out the same way. Okay. And if we run out of time, we'll play with it. So this is my virtual address. Right, if I have to figure out what indexes it will use, well, this is my offset. It won't change. And then I have 9 bits for the rest of them, so I have to turn this whole thing into binary. So A was 1010, B was 1011, and C was 1100, right? So this would, of course, have leading zeros, like everything else in math, so these are all zeros. So if I group them into 9s, this is my L0 index. The next group of 9s, or of 9 ones, is my L1 index, and then the rest is my L0 index, right? So what's my L0 index? If it's all leading zeros? 0, right? Write the resulting number. So that would be 0. What's my L1 index? 6 or 5? The 1's column, the 2's column, the 3's column. So it's 5, right? What's my L0 index? That's a lot of 1s. Well, student reasoning, it must be 188 because it translated correctly, right? If it didn't, if I change this to, what'll happen if I change that to 189 instead of 188? It should page fault, right? It shouldn't have a valid translation. So if I compile and run that, I get a page fault immediately because it would look at the index for 188. It would not have a valid entry, so I wouldn't be able to translate this address. If I change it, I don't know, what comes after C? So if I change it, the C to a D, will this translate now? We have some no faces? Of course it will. Because if I just add 1 to it and the old index was 188, if I just add 1 to it, then it goes to 189, which is what I set, so then I would translate that address or that page. All right.